Welcome to our quantum deep dive.
Great to be here.
Today, we're embarking on a really fascinating journey right to the intersection of two powerful, rapidly evolving fields, artificial intelligence and quantum mechanics.
Absolutely. AI and quantum. This is where things get really interesting.
Yeah, and our goal here at the deep dive, as always, is to, cut through the noise, give you that direct path to being truly well-informed, and really distill those crucial insights from complex research.
All tailored specifically for you, the curious learner.
Exactly. So the subject of our deep dive today is hybrid quantum classical transfer learning for images.
It's a bit of a mouthful, I know.
It is, but it represents a truly exciting frontier, doesn't it? Promising to combine the best of what traditional AI offers.
With the incredible, almost mind-bending potential of quantum computing.
Yeah. And our core insights for this chat come from an excellent essay by Jorgo Schneepat.
That's right. It's titled Hybrids Quantenklasses Transferlernen für Bilder. A really solid piece.
Okay, so let's start with the basics, maybe, but with a twist. Before we even get to the quantum bit.
Good idea. Lay the foundation.
What exactly is transfer learning in the classical sense? And why has it already become such a, monumental game changer in AI?
That's the perfect place to start. Because, at its heart, classical transfer learning is really about taking knowledge gained from solving one task.
Okay, like a source task.
Exactly, a source task, and then efficiently applying that knowledge to a new but related target task.
I see.
Think of it like a really seasoned chef adapting a complex recipe.
Right.
They don't start completely from scratch every single time, do they? They leverage their existing knowledge, ingredients, techniques, flavors, and make smart adjustments.
That makes sense. It saves a huge amount of time and resources, I bet.
An immense amount, yeah.
I really like that analogy. Clicks immediately. So what makes this concept, even the traditional version, so absolutely vital for modern machine learning?
Yeah.
Especially with those, massive deep neural networks we hear so much about.
Well, it's crucial because it tackles several fundamental pain points in AI development.
Like what?
First off, data scarcity. That's a huge one. Training deep neural networks often needs millions, maybe even billions, of labeled data points.
Wow.
And getting, or worse, manually annotating that much data for specific applications. It's often prohibitively expensive or sometimes just plain impossible.
Okay, so data's one thing. What else?
Second, the sheer computational cost. Training these massive networks from scratch is enormous.
Right, the GPU power and time involved.
Exactly. We're talking models with billions of parameters. It demands huge amounts of GPU power, sometimes weeks or even months of training time.
Okay, and you mentioned a third point.
Yes, and this is key. Transfer learning generally leads to better generalization.
Meaning
a model that's already learned general patterns from a huge data set can adapt much faster and more robustly to new, slightly different tasks. It performs better, even on data it hasn't seen before.
it's more adaptable.
Precisely. It's truly revolutionary in practice.
So, given these challenges, the data, the cost, the need for generalization, how does a typical deep learning workflow actually use transfer learning? It sounds like you're not just feeding raw data into a blank network.
Exactly right. The process is actually quite elegant. You start by loading a pre-trained model.
Okay, one that's already been trained.
Yes, usually a very large neural network, like a CNN, a convolutional neural network.
Yeah.
It's already been meticulously trained on an immense, diverse data set. For images, that's often something like ImageNet.
ImageNet, right. Millions of images.
Millions across thousands of categories. So once you have this pre-trained model, you've got a couple of main strategies.
Go on.
You can use it for feature extraction. This basically means you lock the initial layers of the network.
Freeze them.
Yeah, freeze them. You use them as powerful pre-built detectors for fundamental features, edges, textures, shapes, that sort of thing.
Okay.
The output from these layers then becomes the features for your new specific task.
And the alternative?
The alternative is fine-tuning. Here, you slightly adjust the weights of the entire pre-trained network, or maybe just its later layers, to better suit your very specific new data set.
So you tweak it a bit.
Exactly. Finally, you train this adapted model, whether feature extracted or fine-tuned, on your new, usually much smaller, task-specific data set.
Can you give us some concrete examples? Where would we actually see classical transfer learning making a difference today?
Oh, it's everywhere, really. Think medical image analysis.
Okay.
CNNs pre-trained on ImageNet are now routinely adapted for tasks like spotting early signs of specific cancers in X-rays or MRIs.
Wow, okay.
Or detecting anomalies in microscopic tissue samples. It dramatically speeds up development and improves diagnostic accuracy.
That's huge. Any other areas?
Definitely. Satellite imagery, transfer learning helps quickly identify land use changes, urban sprawl, even assess disaster damage.
Ow.
By adapting models trained on general images to these highly specialized aerial or satellite views.
Makes sense.
And in natural language processing, NLP, it's massive. Models like BERT or GPT.
Yeah, we hear about those all the time.
They're pre-trained on vast amounts of internet text, then fine-tuned for specific tasks like summarizing articles, doing sentiment analysis, or powering chatbots.
So it really is the engine behind a lot of the AI we interact with.
Without a doubt.
Okay. So classical transfer learning is already this powerhouse, saving time, boosting accuracy, driving innovation everywhere. But this is where, for me, the conversation gets really exciting. What if we could take this already powerful thing and make it even more capable?
Now we're talking hybrid.
Exactly.
Yeah.
This is where the quantum advantage might step in, where we start talking about hybrid quantum classical models. Why even try to blend these two sort of disparate worlds?
Well, it's really about pushing the boundaries, isn't it? Addressing the limitations that even the best classical AI still faces, especially as data gets more and more complex.
Okay.
The motivation for these hybrid systems is multifaceted. One big hope is reduced computational effort.
Right, faster processing.
Potentially, yeah. Certain quantum algorithms hold the promise of speeding up specific types of calculations, especially when you're dealing with those incredibly high-dimensional data sets common in image processing.
High dimensional, like lots of features.
Exactly. But maybe even more importantly, there's the potential for more efficient and insightful feature extraction.
How so?
Quantum principles like superposition and entanglement.
Oh.
They might allow these models to better recognize subtle, hidden patterns in image data.
Patterns that classical methods might miss.
Precisely. Or patterns they might really struggle to isolate. Imagine trying to spot some faint, complex anomaly in a medical scan. Quantum mechanics might offer a totally unique lens for that.
That's intriguing.
And then, by combining these, let's say, quantum-enhanced features with classical processing, we anticipate maybe even better generalization, making models more robust, more adaptable across different scenarios.
That idea of recognizing hidden patterns is really sticking with me. So how does this hybrid architecture actually work in practice? Is the quantum computer doing all the heavy lifting, or is it more like a specialized helper?
It's very much the latter. It's a collaboration.
Okay.
In a typical hybrid setup, you'll still have a strong classical component, usually a CNN, doing the initial feature extraction from the images.
So the classical network does the first pass.
Right. Think of it doing the foundational work, creating that initial representation of the image, but then a dedicated quantum module comes into play.
The quantum part.
Yes. This module takes the features extracted by the classical CNN and performs a unique quantum transformation on them.
A quantum transformation. What does that look like?
Well, it's like taking those initial features and applying a very special sort of quantum-powered seasoning to bring out entirely new dimensions or nuances.
Okay, interesting analogy.
These quantum transformed features are then passed back to another classical network for the final step, the classification or decision-making.
So it's classical, then quantum, then classical again.
Often, yes. And what's really fascinating here is that the quantum module isn't trying to replace the classical network outright.
It's augmenting it.
Exactly. It's augmenting it, providing a novel perspective, potentially highlighting those subtle nuances or complex correlations that classical algorithms alone might struggle with. It's a true synergy.
So let's drill down into those quantum operations you mentioned. How exactly does quantum mechanics help with this advanced feature extraction? Is it like a super-powered quantum filter?
You could kind of think of it that way, yeah, but it's maybe more profound than just a filter.
Okay.
Instead of traditional CNN filters, these quantum models leverage the unique properties of quantum mechanics using quantum gates.
Quantum gates.
Yeah.
Like logic gates, but for qubits.
Precisely. For example, a Hadamard gate, the H gate, can put a qubit into a superposition of states.
Superposition. Being in multiple states at once.
Exactly. Applied to features, this could let the quantum module simultaneously explore multiple potential interpretations or representations of that feature. It leads to a richer understanding.
Wow. Okay.
Then you have operations like CNOT, the controlled NOT gate. These create entanglement between qubits.
Entanglement, the spooky connection.
That's the one. And it's crucial because it lets the quantum module model complex nonlinear correlations and dependencies within the image data.
Things that classical methods find hard.
things that might be incredibly difficult for classical algorithms to capture, like subtle relationships between pixels far apart that indicate a complex pattern.
I see.
These gates are the building blocks for things like quantum convolutional neural networks, or QCNNs. They're quantum versions of classical CNNs, using quantum circuits for feature extraction.
QCNNs. That sounds incredibly cutting edge and probably complex to build. Are there actual tools out there for researchers to even experiment with this stuff today?
Fortunately, yes. The ecosystem's growing really fast. Several powerful implementation frameworks have popped up. IBM has IBM Qiskit.
Heard of that one.
It's an open source SDK. Lets you design, train, and run quantum circuits on IBM's hardware or simulators. Then there's Penny Lane.
Penny Lane.
Yeah, it's specifically designed for differentiable quantum computing. That means you could integrate quantum circuits directly into classical machine learning workflows using popular tools like PyTorch or TensorFlow.
Oh, that's clever. Seamless integration.
Exactly. And speaking of TensorFlow, Google has TensorFlow Quantum.
Makes sense.
It integrates quantum computing right into the TensorFlow ecosystem.
Yeah.
So yes, the tools are emerging, which is vital for turning these ideas into actual experiments.
Okay, so if we put it all together, comparing classical transfer learning with this emerging hybrid quantum classical approach, what are the absolute key differences you want us, the listeners, to grasp? What's the elevator pitch for why this hybrid thing is distinct?
Okay, let's boil it down. For feature extraction, classical uses CNN filters, right? Which are sophisticated but fundamentally based on linear combinations.
Right.
Hybrid models use quantum gates. They explore nonlinear, multidimensional correlations, superposition, potentially finding deeper insights.
Okay, richer features. What about speed?
Training time. Classical deep learning can be incredibly slow for big models. Hybrid quantum transfer learning holds the promise, and I stress promise,
Right. It's early days.
of reduced training time for certain computationally heavy parts, especially as the quantum hardware gets better.
Got it. And generalization, making the model work well on new data.
Classical models are pretty good at generalization, but hybrid models, by using entanglement, might achieve even more robust and adaptable generalization across diverse datasets. That's the hope.
Interesting. And the obvious one.
The obvious one.
Yeah.
Hardware.
Yeah.
Classical runs on GPUs, CPUs. Hybrid models need access to actual quantum computers.
Which are still rare and expensive.
Exactly. That's a major difference right now.
So what does this all mean for you, the person maybe grappling with real-world data, real-world problems? It sounds like the potential is there for quicker, more accurate, more nuanced insights, especially with really complex image data. You mentioned some application areas earlier. Can we revisit those?
Absolutely. Think about medical image analysis again. With hybrid quantum classical transfer learning, maybe we could see significantly improved early cancer detection.
How?
That quantum module's ability to spot those subtle hidden patterns could literally be a game changer for diagnostics, finding things earlier, more reliably.
Okay, that's compelling.
In satellite image recognition, it could lead to far more precise identification of dynamic land use patterns. Think environmental monitoring, urban planning.
More detail, faster.
Potentially, yes. For autonomous driving, the ability to process sensor data more efficiently, recognize objects with greater nuance, even in bad weather or tricky lighting.
That could drastically enhance safety, couldn't it?
That's the goal. Improve safety and reliability. And even in fields like material science, these models could accelerate the discovery of new materials by analyzing complex molecular structures in ways we just can't right now.
Wow. Simulating molecules and properties.
Exactly. You could revolutionize fields from energy to manufacturing.
This all sounds incredibly exciting, almost like science fiction turning into reality.
It has that feel sometimes, yeah.
But every groundbreaking tech, especially when it's this new, comes with significant hurdles. What are the major roadblocks right now for hybrid quantum classical transfer learning?
You've hit the critical point. The promise is immense, but the challenges are equally substantial.
Let's hear them.
On the technical hardware front, we are still in the very early days. The number of qubits.
Right, how many quantum bits there are.
Yeah. Current quantum computers from IBM, Google, Rigetti, they often have just a few hundred qubits.
Which sounds like a lot, but isn't for complex AI.
Exactly. For truly complex deep learning models, we're probably talking about needing millions of stable, interconnected qubits. We're nowhere near that yet.
Okay, qubit count is one. What else?
Coherence time. Qubits are incredibly fragile. They lose their quantum state extremely quickly because of noise from their environment.
So they can't hold the quantum information for long.
Right. Which makes running longer More complex quantum calculations very prone to errors, and that leads directly to high error rates and noise.
So the results aren't always reliable.
It makes it really difficult to get reliable results from current quantum computers, yeah. It's a major focus of research. And then there's scalability. This is a massive hurdle.
Scaling up the quantum part.
Yeah. Classical deep learning models scale beautifully on GPUs. You can parallelize them.
Right.
We don't really have an efficient way yet to scale up large quantum networks for machine learning.
Why not?
Well, part of it is the nature of quantum mechanics itself. Qubit states collapse when you measure them.
Right.
That makes the kind of iterative training we do in classical neural networks, measure, adjust, repeat, incredibly difficult and resource intensive on a quantum computer.
Okay, so the hardware limitations are definitely front and center. What about the theory side? Are there still gaps in just understanding how quantum machine learning really works or compares?
Oh, absolutely. Big gaps. One of the most significant theoretical hurdles is that there's no formal mathematical proof of quantum superiority specifically for general quantum machine learning tasks.
So we don't know for sure it will always be better.
We don't. While we know quantum computers give exponential speedups for specific problems, like Shor's algorithm for factoring,
Right.
it's not yet formally proven that QML will consistently beat classical ML for all tasks, or even most tasks relevant to deep learning. We need more evidence.
Okay.
Also, the complexity and interpretability of these hybrid models, that's a major concern.
If classical deep learning is already a black box.
Exactly. If classical models are hard to fully understand, integrating quantum algorithms with superposition and entanglement makes them even more opaque.
And that's a problem for high-stakes areas. A critical challenge for things like medical diagnostics, right? Where you need to know why the model made a certain prediction. It's not just desirable. It can be legally and ethically required.
That makes sense.
And beyond that, honestly, we still need better quantum algorithms.
The ones we have aren't quite there yet.
Many current quantum algorithms for machine learning, like variational quantum circuits, are somewhat limited in their expressiveness, their capacity. They often don't yet match the performance benchmarks set by top classical models. We need more powerful, robust quantum algorithms.
Okay, so technical and theoretical hurdles. What about just the practical side of things, getting this stuff used, right? The real-world obstacles. First, cost and accessibility. Huge barriers.
Quantum computers aren't cheap.
Incredibly expensive. They need specialized infrastructure. They're mostly confined to elite research labs or available via cloud services from a few big tech companies.
So not widely available for tinkering.
Not at all. That severely limits widespread use and experimentation. Second, there's a big lack of standardized frameworks.
Unlike TensorFlow or PyTorch for classical ML.
Exactly. For classical ML, we have these mature, widely adopted frameworks. For hybrid quantum classical, there isn't really a seamless, universally accepted way to integrate them into existing development pipelines yet.
Which makes it harder for developers.
Adds considerable complexity and overhead,
Yeah.
And finally, just integration into existing industry applications. That's a huge undertaking.
Companies have invested so much in classical systems already.
Years optimizing deep learning on classical GPUs.
Yeah.
Introducing quantum-assisted models means dealing with compatibility issues. A severe shortage of skilled experts who know both quantum and machine learning.
That's a rare skill set.
Very rare. And you need rigorous, often costly, validation to prove these hybrid models actually provide real-world value over what they already have.
Right, you have to prove it's worth the switch.
Absolutely. So, yeah, this all raises a fundamental question for everyone in the field. How do we as a community strategically overcome these really formidable challenges to unlock the full potential?
Those challenges are definitely significant, no doubt about it, but the potential payoff is also immense. So, looking ahead, what do the glimmers of the future look like? What advancements, particularly on the hardware side, give you hope?
The horizon is actually incredibly exciting, despite the challenges. We're seeing rapid progress in hardware.
Like what?
Major players, IBM, Google, Rigetti, they're actively developing processors with over 1,000 qubits.
Okay, that's a big jump from a few hundred.
A significant leap, yeah. And that increased count is crucial for tackling more complex problems. Researchers are also making real strides in quantum error correction techniques.
To deal with the noise and instability.
Exactly. Designed to combat noise, increase coherence times, leading to much more stable and reliable computations, that's critical.
Yeah.
And we've already seen those quantum supremacy experiments like Google's Sycamore processor showed.
Where a quantum computer did something a classical one practically couldn't.
Right. For a very specific task, yes, but it demonstrated the potential. These hardware advancements are absolutely vital for making hybrid QML practical.
And what about new algorithms? Are people developing smarter ways to use these future quantum computers specifically for transfer learning?
Absolutely. The algorithm side is evolving fast too. We're seeing promising work on things like variational quantum transfer learning, or VQTL.
VQTL.
Yeah, it uses parameterized quantum circuits, kind of like classical networks, use tunable weights to optimize how knowledge is transferred between tasks.
Okay, more targeted learning.
Exactly. There's also progress in enhanced quantum-assisted kernel methods. These are designed to find and exploit complex, nonlinear relationships in data that classical methods struggle with.
Using quantum for the tricky parts.
Right. And researchers are exploring things like quantum neural tangent kernels. These give us a better mathematical handle on understanding the learning capabilities and performance of these quantum-assisted networks.
So better theory to guide the practice.
Precisely. These new algorithms aim to make hybrid models more efficient, robust, and ultimately more useful for real applications.
That's genuinely exciting. So where do you think these hybrid models will first start showing up in industry or science? Where will we, the users or beneficiaries, really see the impact first?
Well, we'll likely see the earliest impacts where even small gains in accuracy or efficiency bring significant benefits.
High-value problems.
Exactly. Back to medical imaging. Maybe vastly improved disease diagnosis, more personalized treatment plans thanks to quantum transfer learning.
Okay.
For autonomous driving, maybe more efficient, robust processing of real-time sensor data, leading to safer navigation.
That's a clear benefit.
In the financial sector, perhaps enhancing complex fraud detection systems, refining risk modeling by spotting subtle patterns classical models miss. And definitely in material sciences, accelerating the simulation and discovery of new materials with specific desired properties. That could revolutionize everything from energy storage to drug discovery. Many big companies are already investing heavily in these areas and looking even further out. The long-term vision is really a profound quantum classical coexistence in AI.
Not one replacing the other, but working together.
Exactly. We're moving towards hybrid cloud solutions, where classical and quantum machines work seamlessly together.
How would that work?
You might see quantum modules evolving into highly specialized coprocessors that accelerate specific, really tough computational bottlenecks within larger classical neural networks.
Like a quantum accelerator card.
Kind of, yeah. Ultimately, you can even imagine AI systems that autonomously look at a problem and decide which parts run best on quantum hardware and which on classical, optimizing everything in real time.
Wow, dynamic allocation.
That dynamic allocation could unlock just unprecedented levels of computational power and insight.
The journey is indeed just beginning, isn't it? But the destination, it promises truly transformative possibilities for how you interact with, analyze, and ultimately understand the world through technology. What a deep dive. That was fascinating. Exploring hybrid quantum classical transfer learning for images.
It really is a cutting-edge area.
We've untacked how it aims to blend classical AI's power with quantum mechanics potential. We've seen how these quantum modules could boost feature extraction, find those hidden patterns,
Offering quicker, potentially more accurate insights.
yeah. And, well, okay, the challenges are significant, technical, theoretical, practical.
They are definitely real.
The rapid progress in quantum hardware and algorithms suggests these hurdles might be surmountable on the path to some truly revolutionary AI.
Indeed. And maybe to leave you, our listener, with a final thought.
Please.
Consider just how quickly classical deep learning went from being niche academic research to this ubiquitous technology shaping almost everything.
It's been incredibly fast.
So what new frontiers of insight and capability will truly open up when quantum computers, which are really in their infancy, now become an integral, seamless, and widely accessible part of AI's core infrastructure? The possibilities aren't just immense, they feel almost limitless, don't they?
That is a truly powerful question to ponder, and it really highlights the incredible journey ahead. We hope this deep dive has given you a clearer picture of this complex but utterly captivating subject.
Hopefully spark some curiosity.
We definitely encourage you to continue your own exploration. Our thanks today go to Jorgo Schneppet for his insightful essay, Hybrids Quantum Klassisches Transferlernen für Bilder, which really formed the backbone of our discussion.
A great resource.
And you can find more information about his work at schneppet.de. That's SCHNEPPAT.de.
Check it out.
Thank you so much for joining us on this deep dive.
Thanks for listening.
Until next time.